Hey guys, what's up? Today I'm going to show you how to use DeepQ networks, which is a type of deep reinforcement learning, to balance this card poll. So let's get started. Before we get started though, I do need to mention that you need to be a bit familiar with reinforcement learning in order to grasp everything in this video. But if you're not that good at it, it's okay. I'm going to explain all the concepts as best as I can, as easy as I can, so that you can understand it even though you're not that familiar with reinforcement learning. So to get started, deep reinforcement learning uses neural networks, which is able to capture complex behaviors and relationships. So we use deep neural networks for our decision making. We basically pass a state of the environment, which explains what the agent sees. And for this environment, it could be the position of the card or the angle of this pole. So we pass all these data points into the neural network, and the neural network basically tells this card what kind of actions to take, whether to go left and right. And so that is basically that. And so it's pretty simple. We use experience replay to capture all our experiences or store our past experiences, and then we learn from them. We also have two instantiation of this neural network. One is the policy network, the other one is the target network. So most of these concepts are pretty straightforward, except I would say, why is there two different types of network? And to explain this, I've used an analogy. So think of learning how to shoot a basketball. The policy network is you trying to shoot the basketball. The target network is your coach who demonstrates the perfect shot. So the policy network, is trying to mimic your coach's shot. The target network, initially your throws aren't very accurate, so explore multiple different option techniques of shooting and assess how far each one of those was from the perfect shot. Based on the feedback, you adjust your technique and improve your next attempt. So that's kind of why we need two different networks. One is basically one demonstrates the perfect shot. The other one is trying to mimic the perfect shot. But anyways, let's get to the code and hopefully it will make a bit more sense. So in order to code, we need to import a few modules. We need to import Gymnasium, which will give us access to the environment. We also need to import Torch, NNN, torch.optim, import collections from collections, import EQ, import random, and import ampy. So if you don't have any of the package, make sure you have all of these packages installed. Afterwards, we will make the environment by calling gym.make, and the name of the environment is cardpoll-v1. So the environment, and we can do a couple of cool things. Once we have access to the environment, we can print the observation space, and we can also print the action space. And these things are important to know in order to build the neural network. So as we will see, the observation space tells us what kind of data points we'll observe. So this first data point ranges from this value to this value, second data point, third data point, fourth data point. So we get 4 different data points at each observation we make. And then we can either take two action, either go left or go right. So knowing this, we then can create a neural network. The class network is nn.module def init cell input size is 4. Because we have 4 different data points, output size is going to be 2, and hidden size, how many hidden neurons we want, we can set this to arbitrary 42. So network self.init, I'm just going to use self.net is nn.sequential. I'm just going to use the sequential to create this network. So it's going to take an input size, it's going to go output hidden size, it's also going to do a ReLU activation. Pretty simple network. You can make it more complex if you want, but I'm just going to keep it pretty simple. ReLU. And we need to just make this network a few layers deep so it can capture more complex relationships. I'll just paste this a few times. I think that should be good enough. And then the linear, it's going to take a hidden size, it's going to output an output size. That looks good to me. Then we need to write a forward function, which will basically take some input size, take some input data, and then forward it and return it back to the user. And that's the network. And as I said before, we need two instantiations of this network. One is the policy network, which is network 42. The other one is the target network, is network 42. And the policy network and the target network, they need to have the same weights and biases initially. So I'm going to do target network dot load state dict, policy network dot state dict. And the reason for this is because the policy network and the target network the target network is basically a copy of the policy network, but because we want to stabilize the learning of the policy network, we copy the weights and the biases to the target network and every so into a few intervals. Cool. So after that, we can then create an experience replay. So just define a class called experience replay. Now it's a good idea to define a capacity as well, because you don't want to store every single experience possible. Otherwise you'll run out of storage very fast. So I'm going to define 5,000 capacity, which should be enough for our agent to learn. And DQ max length is capacity. We should also define a function to push experience self.memory.append x sample from experience self.n. We need n samples. Random.sample self.memory n. Def length self return length of self.memory. So that's basically our experience replay. It's going to allow us to push experiences into this buffer and also allow us to do random sampling from the experience, which is crucial for training the network. So then we can go ahead and train the network. So to do this, we need to create a loop. This loop is basically how many times we want to train the network. And I'm also going to create an instantiation of this experience replay. So memory is experience replay, and then the loop, how many episodes we want to train, how many episodes we want to train. So for episode in range for this environment, we can go up to 400, which is quite good. 400 is good. So every time we're going to reset the environment to its initial position. So we are going to basically reset this pole into its initial position, which is pole standing up straight and the card in the middle. So to do this, we're going to say state equals to env.reset. And if I just print out the state so you can see it, we will have the initial state as data points. So these data points represent the initial state. And as you can see, there are 4 different data points. So after we have that, we also need to do total rewards to keep track of how many rewards we're getting. After having the initial position, we can then go ahead and start taking actions. So I'll write another loop for timestamp in range. This loop can be really long because we will take action until the end of the environment. So it doesn't matter how long this loop is, but just an appropriate number. I've set it to 10,000. And so to take an action, we're going to use the epsilon greedy algorithm. So the epsilon greedy algorithm is, we need to first define an epsilon. Epsilon is equal to 0.01. So this is the minimum epsilon plus 0.9, the maximum epsilon minus the minimum epsilon, multiplied by np.x. Did I import numpy? Yes. numpy.exponential 1.0 multiplied by the number of steps we've done. So total steps done. This total steps is going to increase every time we take an action. So I'll do 1 + 1. Total steps done divided by ideally how many episodes we will take. So I'll just set it to 400. Now this epsilon, it basically exponentially decreases from 0.9 all the way to 0.01, and it reaches 0.01 at the 400th step. So hopefully that makes sense. If you don't really know what this is, you can do a little bit more research, but this algorithm we will use is called epsilon greedy algorithm. So after having epsilon, we will do if random.random. This will give us a random number between 0 to 1. So initially, because epsilon is going to be really high, the chance of us getting a higher number than epsilon is going to be really low. So then if epsilon is greater than epsilon, we're going to take greedy action. Else we're going to just explore and take the non-greedy action. So take random action. So initially our agent is going to try to explore different techniques, but after it has explored some different techniques, after a few steps close to 400, we're going to try to take the action that we think will give us the best result. And so to do that, we need to first make this state into a tensor. So do torch.float tensor state before we pass it to the network. Then we will do action. So this will represent the best action. We will do policy network state.argmax. It's going to give us, so this policy network is going to return 2 values. Now we want the value that is the maximum. So we're going to take, this is going to return the index for the value that's the that is the highest value. So if the first value is the highest, it's going to return 0. If the second value is the highest, it's going to return 1. And then we want the item, which is going to be basically the index. So the higher value means that state, taking that action is more valuable than taking the other action. Otherwise, we'll do action is np.rand random.rand range 2. And so that's basically the action bit. So after we determine which action we're going to take, we can do next state reward truncated, actually terminated truncated equals without step action. So then we will take the action, and after we take the action, we'll get a couple of values back. We'll get the next state, if we got how many rewards we got, whether the next state was a terminal state. So the terminal state basically means if it was the end, or if it was truncated, meaning our agent prematurely finished by dying sooner than expected. So after that, we need to push all of these into our memory. And to do that, I'm going to do memory.push state next state action, and I'll define a new variable called done is equal to terminated or truncated. So we'll do terminated or truncated. So we'll push it to the memory, and then we'll keep collecting experiences. We need a certain number of experiences in order to train the model. In this case, I'll choose 64. I'll say if length of memory is less than 64, I'm going to continue. So I'm going to continue collecting experiences, but if it isn't, then train the model. So in order to train the model, we need to sample from the memory.sample 64, and then I will also do zip experiences. Now what this does, it basically separates all the states into one list, all the next states in another list, all the actions in another list. So it creates a different list for each of these things here. So then we can do states is equal to batches.0, and let me just show you guys what this prints out. Memory self, I need to return that. So there we go. It just so these represent all the states, and we need to, in order to train the model, all the states have to be in a tensor format. So I'm going to apply torch.float tensor states. Next state is torch.float tensor batches 1 actions is torch.long tensor, because we don't want it to be in a float format, we want it to be in integer format. So torch.long tensor actions batches.0.1.2, and we also need to add another dimension to this, which we will see why later. So if I print actions break, there we go. So all the actions are actions. There's been an added dimension to all the actions, so each element is inside a list. So that's what the unsqueeze function does. And term done is torch.float tensor batches 3. So state next state. Did I push rewards? State next state rewards. I also need to push reward. Terminated done reward. Rewards is torch.float tensor batches 4. And we need all the rewards. I'm just gonna run this to make sure everything's good. That seems okay. I re-recorded this part of the video because I realized I made a mistake. So this is supposed to be -1. I previously had it as +1. So just change that. And next we're going to calculate the predicted Q values for our state action pairs. So to do this, we're going to say state action values is equal to policy network. We're going to pass the states, then we're going to use this method to get the values for the actions that we've taken. And we're going to calculate the Q values for the next states. We're going to use We're going to use the target network for this. So next state action values is equal to target next states, and we're going to take the maximum for the maximum Q value for the next states. And we obviously know that if the next state is the terminal state, then the Q value is going to be basically 0. Then we can calculate the expected Q values by combining the immediate reward with the expected future rewards we may get. So to do this, I'm going to say expected return is equal to rewards plus next state values times 0.9, and that's basically the discount factor. Then we're going to make a loss function. Loss is nn.functional, and we're going to use mean squared loss, and we will need the state action values and squeeze, and we also need the expected return. Loss.backward optimizer. Before we do loss.backward, I need to do optimizer.drag, zero out the gradients, and optimizer.step. Oops, I don't know what happened there. So I think this should be all good now. Actually, the next if done, we are basically going to break out of the loop. But before we break out of the loop, we're going to print the episode and also the total reward that we got. Total rewards. What is happening? Wait, never mind. Okay, total rewards. We're going to break out of the loop. We're going to say state equals next state. Yep, so then we need to update this state so it equals to the next state, and I think that should be good. We also need to update this target network every so interval. So I'm going to say if episode equals to 0 target network state dict policy network state dict. So since this target network is a copy of this policy network, we need to basically update it every so interval. The policy network changes all the time, but the target network is a stable version of the policy network, and so this is why we need to make sure we update the weights and the biases for the target network at every so intervals. And so let's run this and see if it's working fine. And I forgot to update the total rewards. Total rewards is equals to plus equals reward. Let's see. And as we can see, the network is improving, in fact. So as we get closer to more episodes, the network improves and it gets more rewards, so that's good to see. Now let's actually see that visually. So I'm going to say env gym.make. We're just going to remake the environment, redefine the environment carpol-v1, and set the render mode is equal to human. Now the loop is going to look the same. So I'm just going to do episode for 8 range equals, maybe let's try 10, and for timestamp in range action is equal to policy state argmax.item. So we're going to take the best action possible, and then we're going to say next state reward terminated truncated equals step action, and then equals next state. So I think that should be good. Yep, so this is just rendering it for us to see, and I obviously need to see if terminated or truncated. We're just going to break out of the loop. So let's try it. Fingers crossed. So the network is improving. That's good to see. Okay, and it says I need to do state equals a torch flow tensor state. Let's try that one more time. Fingers crossed. Hopefully it works this time. But as we can see, the network is improving, so it's able to learn those complex relationships, and it's able to learn how to balance the pole. And as we can see, it can balance the pole, right? The pole is leaning to the left, and it's moving to the left in order to balance the pole. Now we can train this a bit more, and we can use a more complex neural network, but so far it's doing really well. It's achieving some good results. Anyways, I hope you guys enjoyed that, and I hope you learned something, and I hope it sparked some inspiration. If you like content like this, then subscribe and like this video so that I can make more videos in the future. Thank you.